Hi guys!
Welcome back. So William, I'm going to ask you a question, okay?
Okay.
I'm going to consider a titration reaction where I'm going to place NaOH into the burette,
Okay.
as well as ethanoic acid into the conical flask. So we're going to let the burette run, and of course when the indicator turns color permanently, that's where the endpoint is reached. I'm going to stop the titration.
Yes.
Now I'm going to give you the conical flask.
Alright.
I'm going to ask you, what is the pH that is that's going to be in the solution?
So at the endpoint or equivalence point, you're saying that the number of moles of base should be the same as the number of moles of acid. That means at that point, there's only going to be salts left.
Okay.
And if there's only salts left, salts are expected to be neutral.
Okay.
Therefore, I would think that the pH of the solution, it is 7, isn't it?
Okay, so let's take a look. We're going to see whether it is true.
Okay.
So actually what I have here is basically the salt solution. Right? This is done after titration, okay? Now, what I'm going to do is I'm going to add the indicator. Okay, so this is the indicator. It is purple in color.
Yep.
This is going to be the color at neutral. So if it turns acidic, it is going to turn red.
Okay.
But if it's alkaline, it is going to turn green. So
Okay.
can you tell me, based on your prediction, what color do you expect to see?
So I'm expecting this to be neutral, right? So when you add that reagent in, the indicator in, this thing is going to be purple, right? So that it's neutral.
Okay, so let's take a look whether it's true.
Okay.
So I'm going to add the indicator into the salt solution, and let's take a look. William, what color is this?
Purple?
Are you colorblind?
No, you're the one that's colorblind.
Can you tell me the correct color? I really cannot see.
Okay, this is kind of strange, but it's like greenish.
Okay, so what does that mean?
Greenish means this thing is kind of alkaline.
Are you surprised?
That can't be true, because salts are expected to be neutral.
Okay, so why is it that it's going to have other, whether it's acidic or basic? We're going to refer back to the notes.
Yeah, it's quite confusing, right? I mean, then how does a student know whether a salt is going to be acidic, basic, or neutral? Is there a strategy or a way for us to know?
Sure. So we're going to take a look at the notes. But before that, we'll need to explain a little bit, or to recap a little bit, that something we have learned earlier. That is coming onto this notes over here. Tells us that if you start off with a strong reagent, then its conjugate will always be weak. And of course, the vice versa is true. Now let's take a look at the salt that we have produced earlier. That is your sodium ethanoate. And in order to determine whether is it acidic, neutral, or basic, we're going to follow 3 major steps. Step 1 is to generate a full dissociation equation to show me what are the ions that are present in the salt solution. Now step 2 is going to be a little bit weird. That's where you're going to start to take a look at what are the acids and bases that creates these ions. So William, the ethanoic ion, can you tell me where did it come from originally?
Okay, so I'm expected to work backwards to know what is the acid or base. Okay, so ethanoate looks like it comes from ethanoic acid.
That's right. And can you tell me ethanoic acid is what kind of acid?
It should be an organic acid. So organic acids are weak acids.
And if that's the case, can you tell me something about the conjugate, which is the ethanoic ion?
That's something we learned in the first lesson, right? So a weak acid should have given rise to a strong conjugate base.
That's right. And let's extend this idea to sodium plus.
Okay.
What kind of reagent that we use that produces Na plus?
It should come from NaOH,
which is a
strong base.
That's right. And can you tell me something about the Na plus then?
If a strong base, then it should give rise to Na plus, which is a weak conjugate acid.
That's right. Okay. Now, if I take a look at the 2 conjugates, can you tell me which one do you think you will focus on?
If there's one strong, one weak, naturally we're going to focus on the strong guy.
Yes, that's right. So we're going to look at the strong conjugate base, and this is exactly the reason why it's going to give me a basic solution. So the last step, which is to go and write out the equation that represents that reaction, is going to be given here. So you tell me that if it's a base, right, William, what does a base usually do?
A base is expected to grab proton, something we learned again from the last lesson, right? So in this case, it is going to grab proton, I think, from water.
Yes, that's right. So the H2O is going to give up a H+, and as a result, your ethanoate ion will become back the ethanoic acid. But more importantly, we notice that you are going to release a OH-, right? So in this case, William, what kind of reaction is this?
I think we call this hydrolysis. All right. I think the word hydrolysis comes from hydro, which stands for
water,
and lysis, that stands for
breaking down.
So you can see that the water is kind of broken down into H plus and OH minus, and H plus is going towards that base, right? And you leave behind OH minus. That is why the solution becomes basic in nature.
That's right. So that's exactly the reason why. So in the context of Na plus, unfortunately, because it is considered to be a weak conjugate acid, you do not find Na plus undergoing any form of hydrolysis.
Alright, now, so these are the 3 steps. Okay, I'm going to try to use the 3 steps to try to solve for another salt and see whether that works or not. Okay, so step number 1, we were saying do a full dissociation. Alright, so NH4Cl is going to ionize to give us NH4 plus and Cl minus. This is step 1. Now, the second step is for us to work backwards. Okay, so we're going to work backwards. NH4 plus would have come from?
Ammonia, NH3, which is a weak base.
Okay, this is a weak base.
And that's going to cause my NH4 plus to be a strong conjugate acid.
Okay, so this is going to be a strong conjugate acid. And Cl minus would have come from?
HCl, which is a strong acid. That will make my Cl minus a weak conjugate base.
Okay, so I have done step 2, which is working backwards. And then I have 1 strong and 1 weak. So what do I do?
Focus always on the strong, which is the NH4 plus.
Okay, so I'm going to focus on the strong guy, and this time round is an acid. So the job of an acid?
It is to give out H plus.
Okay, it's to give out H plus. So we have to write an equation. So this is the strong guy, and what is he doing? He's going to release 1 H plus towards water. So the end result is you're going to form ammonia as well as H3O plus. So because of H3O plus that's being released, that's how we know that the solution is going to end up acidic in nature.
That's right. So that's going to be the third step, writing out the hydrolysis reaction. So once again, pay attention to the fact that it must be a reversible arrow. Now, honestly, William, I think you're very lost all there. I think I want to go for a shortcut, right?
Okay.
So I noticed that if I look at the final solution, which is acidic, you do realize that it corresponds with the strong acid HCl over here. So this tells me that the moment I take a look at the reagents, what I start off with, I should be able to predict what is the solution going to be like. So I think of it as HCl as the daddy, the NH3 as the mommy, and the salt over here would just be the baby.
Okay.
So imagine if you have a daddy who has a strong trait, a more dominant trait, which I call this the strong acid.
Okay.
And the mommy is going to be the weak base. Can you tell me for the kid, do you think the kid will be acidic or basic?
It will follow the stronger parent, right? So in this case, then it will follow more like the daddy who's a stronger guy. That's why if daddy is acidic, then we expect the child to be acidic in this case.
That's right. So therefore, it's always going to follow the more dominant reagent, which is the strong reagent. Now, if you don't believe me, you can take a look at the previous case. It's going to be the same thing as well. So I have a strong base and a weak acid. So the mommy is stronger. Sorry. The mommy is stronger now. So it should not become as a surprise that at the end of the day, the baby will also follow the mommy, which means that it's going to become basic. Now the last one that we're going to see is going to be of NaCl. Now, William, let's run this through again using my shortcut. Okay. So we're going to write the equation. That's step number 1. Step number 2, we're going to work backwards. Can you tell me the 2 reagents that you create, that helps you to create the ions?
Okay, so we come from NaOH. That is a strong base.
That's right.
And then we have HCl, that's going to be a strong acid.
Strong acid, that's right. So in this case, both the daddy and mommy are strong. So what do you think the kid will be like?
The kid will be half daddy, half mommy.
Huh? Oh, okay. What does that mean?
It means it's neutral.
Yes. So this is going to be something that is a little bit special. If both reagents are strong, the final salt will be neutral. Now, it's your time to take to try out these steps. So if I take a look at the quick test at the bottom, can you pause the video and try out these first 4 examples? And then after that, once you're done, we're going to continue with the explanation.
Hi guys, welcome back. So you should have tried the 4 questions. Okay, I'm going to use that same method, the shortcut method that Mr. Leong has shared with us to try to solve for these 4 questions. Now the first question you're looking at is KBr. Now KBr came from KOH, which is going to be a strong base, and it also comes from HBr, which is a strong acid. Since both are strong, then this thing is going to be neutral. Alright, now the second question, now this looks a bit weird, but this is actually what we call a phenoxide. Now phenoxide comes from?
Phenol, which is an organic acid, because you see that there's going to be carbon inside, so therefore it's definitely going to be a weak acid.
Yep, this is how we draw phenol. Now some of you guys, you may not have learned this yet, but you can see that there's a carbon containing species, and that's why we know this is going to be a weak acid, together with Na+, that came from NaOH, that is a strong base. So you follow the stronger guy, and hence we know this salt is going to be basic in nature. Right? Now the third one, Na+ again is going to come from NaOH, and we have Cn minus. Now, Cn minus would have come from HCN. And what's the nature of HCN?
Once again, it's carbon containing, so no doubt it's going to be a weak acid as well.
Yes, right. So what we have here is we have actually a strong base together with a weak acid. So again, you follow the stronger guy, and this guy is going to be basic in nature. Okay, the last one, whenever you see structures like this, this is actually what we call amine containing species. So this thing comes with a positive charge and a Cl minus. Right, this came from organic base. All right, so the starting material for this, it will be CH₃NH2. So what he did was he accepted one H plus to form this salt. And the nature of this guy being organic must have been a
weak base.
Okay, so this is going to be a weak base, and therefore Cl minus would have come from HCl, which is a strong acid. So at the end of the day, you will get a salt that's going to be acidic in nature. So that's it. You can see, right, the shortcut method for us to know whether a salt is acidic, basic, or neutral, it is actually quite simple. Okay, so we're going to leave you with 4 more questions for you to self-attempt. So when you come back to class, our teacher is going to explain the 4 salts to you guys. All right, so we'll catch up with you in class very soon. Take care and bye.